Quantum retrocausality. This is what we'll be discussing today in our deep dive. Quantum retrocausality is a theoretical concept in quantum mechanics that posits the ability of future events to influence past occurrences, challenging traditional notions of causality and time. This idea has garnered significant attention for its potential to reconcile the apparent contradictions between quantum predictions and classical intuitions, offering a radical re-examination of our understanding of causation, measurement, and the nature of reality itself. As researchers explore this framework, it raises profound implications not only in physics, but also in philosophy, particularly regarding the nature of time, free will, and moral responsibility. At the core of quantum retrocausality is the notion of instrument non-contextuality, which asserts that operationally indistinguishable outcomes in quantum experiments should also be indistinguishable at an ontological level. Proponents argue that retrocausality can provide solutions to various no-go theorems in quantum mechanics, suggesting that causal relationships are inherently time-symmetric and can incorporate influences from future events. The transactional interpretation of quantum mechanics exemplifies this idea, illustrating how handshakes between quantum states can occur in both temporal directions, thereby supporting a framework where causality loops may manifest in quantum interactions. Experimental evidence for retrocausality has been highlighted through a series of delayed choice experiments, such as done by the notable Kim-Chan-Scully quantum eraser experiment, which demonstrates that measurement choices made after the detection of a photon can retroactively influence its earlier behavior. These findings challenge classical interpretations of causality, suggesting that the flow of time may not be as linear as traditionally conceived. Critics of retrocausality often demand more direct experimental evidence to substantiate its claims, while supporters argue that existing experiments already point toward its validity as a robust interpretation of quantum phenomena. Philosophically, the implications of retrocausality extend to deep questions about free will and the nature of agency, as the idea that effects can precede their causes complicates established notions of accountability and moral responsibility. That's pretty deep stuff. Historical opposition to retrocausality has included critiques from notable philosophers, which underscores the contentious and evolving discourse surrounding this paradigm. As the investigation into quantum retrocausality continues, it invites a transformative perspective on the fabric of reality, encouraging scholars across various disciplines to reconsider fundamental assumptions about time and causality. The theoretical framework. Quantum retrocausality challenges conventional interpretations of quantum mechanics by suggesting that future events can influence past occurrences. This concept can be framed within the ontological models framework, which provides a structural foundation for evaluating various realistic models in quantum mechanics, including classical theories and local hidden variable approaches. At the core of retrocausal theories is the idea of instrument non-contextuality, which posits that operationally indistinguishable outcomes should also be indistinguishable at the ontological level. This principle implies that the contextual nature of quantum systems extends beyond just states to encompass other fundamental features, such as dynamical laws and boundary conditions. Shrapnel and Costa argue that no instrument non-contextual model can accurately replicate the statistical predictions observed in quantum experiments, suggesting that the relationship between measurements and their outcomes is inherently contextual. Retrocausality serves as a potential solution to circumvent the limitations posed by various no-go theorems in quantum mechanics. By allowing future conditions to influence past events, it provides a framework that can reconcile the apparent inconsistencies between quantum predictions and classical intuitions. The transactional interpretation of quantum mechanics, for instance, emphasizes the significance of transactions or handshakes between quantum states evolving in both time directions, showcasing how causal loops can manifest in quantum interaction. In this context, the operational statistics derived from quantum experiments must replicate the quantum statistical outcomes supporting the notion of retrocausal frameworks as viable interpretations. The emphasis of retrocausal models lies in their ability to align operational descriptions of measurement processes with ontological accounts that respect causal relationships. Such frameworks suggest that dynamical laws are time symmetric, indicating that causal models must also accommodate retrocausal elements to fulfill the empirical requirements of quantum theory. A contemporary interpretation that encapsulates these ideas is the relational block worldview, which posits a reality composed of space-time source elements that intertwine space, time, and causal relationships. This interpretation aligns with retrocausal theories as it acknowledges the interdependence of past, present, and future events in shaping the observed phenomena of quantum mechanics. Thus, the theoretical framework of quantum retrocausality invites a re-examination of foundational assumptions regarding causality, measurement, and the nature of reality itself. Experimental evidence for retrocausality has gained significant attention in recent years, particularly through a series of delayed choice experiments that challenge traditional notions of causality. The concept of retrocausality suggests that effects can precede their causes, which poses philosophical and scientific challenges to our understanding of time and causation. The first notable investigation into retrocausality began with Carl Ali, Oleg Jakubowicz, and William Wicks in 1984, who conducted a delayed choice experiment at the University of Maryland. Their findings supported John Archibald Wheeler's hypothesis, indicating that a photon's behavior, whether it manifests as a wave or a particle, can be influenced by measurement choices made after its detection. This suggests a retroactive influence on the photon's prior behavior, a notion that profoundly complicates classical interpretations of causality. Subsequent refinements were made by Helmut, Walter, Zajonc, and Schleich, oh, I can't pronounce his name, in 1987, who emphasized that these results highlight the inadequacies of classical explanations for quantum phenomena, thereby reinforcing the implications of retrocausality in understanding quantum mechanics. The Kim-Chan-Scully delayed choice quantum eraser experiment in 1999 provided a particularly striking demonstration of retrocausality. In this experiment, the researchers established that the decision to obtain or erase which path information about a photon could be made after the photon had been detected. Their conclusion emphasized that the choice to observe wave or particle characteristics could occur retroactively, further challenging conventional temporal sequences in quantum mechanics. The implications of these experiments are far reaching. They have been interpreted as evidence against local realism, suggesting that distant particles can exhibit correlations without direct physical interaction, thus posing challenges to Albert Einstein's theory of special relativity. Ow. The experimental outcomes have been deemed significant enough to merit a Nobel Prize in Physics, underscoring the ongoing investigation into the nature of causation and the quantum realm. Critics of retrocausality often demand direct experimental evidence, yet proponents argue that existing experiments already provide a compelling case for considering retrocausal interpretations as valid explanations of quantum phenomena. This ongoing discourse points toward a broader re-evaluation of time's nature in light of quantum mechanics, advocating for the acceptance of retrocausality as a viable framework for understanding the complexities of the microworld. The concept of retrocausality raises significant philosophical questions regarding the nature of time, causality, and free will. Retrocausality suggests that effects can precede their causes, which challenges conventional understandings of temporal order and causative relationships in both physics and philosophy. This notion posits a framework where future events can influence past occurrences, creating a bidirectional flow of causality. Philosophical opposition to retrocausality has historical roots. In the 1950s, philosopher Michael Dement contended that there was no inherent philosophical barrier to the idea of effects preceding their causes, a viewpoint that faced criticism from contemporaries such as Anthony Flew and Max Black. Black's Bilkin argument claimed that retrocausality is untenable because an observer witnessing an effect could potentially intervene to prevent its future cause from happening. Such critiques illustrate the contentious nature of the discourse surrounding retrocausality. In addition to challenges related to temporal order, the implications of retrocausality extend into discussions about free will and moral responsibility. The notion that effects can occur before their causes raises questions about agency and accountability. If future decisions can retroactively influence past events, it complicates traditional narratives of causation, which typically underpin concepts of free will. Philosophers have examined these implications, proposing various theories that grapple with the idea of genuine causal powers within nature, thereby questioning the foundations of induction and causal reasoning in understanding the universe. The ontological models framework offers a perspective through which retrocausality can be analyzed in relation to contextuality. According to this framework, no non-contextual ontological model can replicate the statistical outcomes observed in quantum experiments as hypothesized by speculants. This principle suggests that the very structure of quantum mechanics may necessitate a re-evaluation of how causality is perceived, especially when retrocausal interpretations are considered. Recent advancements in the field have attempted to recast the principle of parsimony to apply more broadly to retrocausal models, thereby engaging with the intricacies of contextuality in quantum systems. Quantum retrocausality has profound implications across various fields, from theoretical physics to philosophy and even quantum computing. Researchers are exploring its potential applications in multiple areas, including experimental design, philosophical inquiry, and technological innovation. In the realm of technology, retrocausality is being considered in the development of quantum computing. Insights from retrocausal theories could enhance our understanding of quantum data loading and improve the efficiency of quantum algorithms. Researchers have indicated that quantum systems might leverage retrocausal mechanisms to process information in a nonlinear fashion, potentially achieving faster problem-solving capabilities compared to classical computing models. For instance, the ability of quantum computers to reach into the future for answers is being examined as a means of improving computational efficiency. Imagine when we're capable of reaching into the future for someone's, I don't know, Bitcoin wallet, private key. One of the primary areas of application for quantum retrocausality is in the design and implementation of experiments in quantum mechanics. The exploration of retrocausal models may lead to novel experimental setups that could test the limits of our current understanding of time and causation. For instance, researchers have proposed using automated systems to conduct experiments that manipulate time intervals, allowing for deeper investigation into the nonlinear effects of time on quantum behavior. This includes setting up experiments that systematically vary on duration times from 60 seconds to an hour, thus creating a more robust dataset for analysis. The philosophical implications of virtual causality extend significantly into the understanding of time and causation. Philosophers like Dean Rickles have posited that quantum mechanics may suggest a block universe model of time where distinctions between past, present, and future blur. This perspective encourages a re-evaluation of concepts like free will and determinism, as it implies that future actions could influence past events. Such philosophical discussions challenge our traditional linear view of time and causation, leading to a rethinking of fundamental concepts in physics. That's very interesting. Oh, there's no one here.